Hello, let me reintroduce Lindsay DeMarchi, still coming from Northwestern University with a very intriguing and macabre title.
Thank you. Um, I had definitely planned when I came up here to thank the planning committee and Gotham especially for all the fun they clearly had while planning. And then I promptly made that not fun. So thank you for still having fun and still smiling. And thank you so much, Dylan, for sacrificing 20 minutes of practice for everything. So thank you. I'm Lindsay DeMarchi. I'm a grad student right now at Northwestern University, and I have the immense pleasure of being the mentee or student of two different grad school advisors. So Rafaela Margutti from UC Berkeley and Shane Larson at Northwestern. I do multi-messenger astronomy, and I'm particularly interested in core collapse supernovae, but I also work all across the electromagnetic spectrum. So I do multi-wavelength and multi-messenger astronomy. But today, especially, I wanted to talk to you about the ways that LSST and radio astronomy can do some very, very powerful things, especially regarding the very final moments of core collapse supernovae and supernovae in general, as it turns out. But before I get into that, I need to tell you what's been broken. All stars throughout their lives have material, have elements in their atmosphere, and particularly the electron orbitals of those elements have a lot to do with the way that a star behaves throughout its life. And so you have electrons around these nuclei, and they're in their orbitals, and every once in a while a photon comes in, and that photon interacts with the electron. It increases in a energy level. And what actually happens on the grand scale of the star itself is that you have a net momentum away from the surface of a star in a phenomenon that we call mass loss very generally. But what's really happening is the momentum from these photons and from these electrons moving in their orbitals of these materials are actually causing the material in a net angular momentum to move, or sorry, just momentum to move away from the surface of the star. That was a long-winded way of saying m dot, that's mass loss. And if it depends so highly on the number of electron orbitals and the number of photons, then perhaps it's no surprise to you that this depends very heavily on metallicity. So Z here is metallicity, but that's just like saying the number of orbitals that are around a nucleus. I also mentioned the photons. That was the only other thing I said. And that's directly related to luminosity. So here L6 is a shorthand way of saying 10 to the 6 solar luminosities, very, very luminous. But if a star has a strong metallicity or strong luminosity, then you can expect a lot of mass loss due to this particular mechanism. The name of this mechanism is line-driven winds because it is so metal dependent that when you look at it spectroscopically, you see metal lines. So it has the nickname line-driven winds. If I plug in solar metallicity and 1 for L6, then rounding up, I get a limit of 10 to the minus 4 solar masses per year. What this means is that this mechanism that we think all stars experience can be responsible for 10 to the minus 4 solar masses of material per year, and that is an upper limit. So nothing more than this from line-driven winds. And this is one of the only things that we're reasonably sure about. We know that stars throughout their lives lose material, and we see it in real images. So this is my favorite picture that Hubble has ever taken. And this is actually a Wolf-Rayet star that has lost mass. It's still living. So departures from line-driven winds, I think, are pretty well known at this point. So one of the most popular, because my advisor did so much, so it's popular to me, but you may have never heard of it before. It's 2014C. Actually, a lot of you here have worked on this, but 2014C was a type 1b supernova that in its circumstellar environment, as the supernova exploded, crashed into a solar mass's worth of material, a shell that is a solar mass, about 10 to the 16 centimeters away from the star. If line-driven winds have a maximum rate of 10 to the minus 4 solar masses per year, a single solar mass of material is a ton that cannot be chalked up to line-driven winds, at least not easily. The other remarkable thing about it is that it's a shell. And the mechanism that I was describing about line-driven winds, it's a steady, constant process. So the notion of a shell existing or any kind of structure in the CSM doesn't make sense if this is the underlying cause. For my PhD, I worked on an extremely similar namesake called 2004C, that is a type 2b supernova, but also crashed into material in the CSM. And rather underwhelmingly, it was only 2/100ths of a solar mass. So when I integrated this curve and figured out that was how much, I was very disappointed because I was very much looking forward to a solar mass worth of material. But if you think of a star losing 0.02 solar masses per year, that star can only live about a couple thousand years reliably. So this is still an extremely high amount of mass loss to be losing that doesn't really point to a stable underlying process. A star can't stably lose that much material every year and still survive. Again, at 10 to the 16 centimeters away from its explosion site. So the plot that you're looking at is density on the y-axis, and on the x-axis is the radius away from the explosion. So to your left is where the star exploded, and to your right is infinity. And what you are looking at, with no imagination required, is the density profile in the CSM of the star. So this is real radio data, those data points that are up there with error bars on them. And what you are looking at is the density profile as it falls off. So close to the star, you have some kind of dense horizontal structure, or horizontal in density space. And as it tapers off, it starts to resemble a constant line-driven wind. So, or I shouldn't say line-driven wind, just a constant wind in the CSM. And so if it had been constant throughout its life, that rate would correspond to any of the dotted lines that I've drawn in the background. So the gold line to guide your eye is the outer portion of this shell that's located at 10 to the 16 centimeters, and you see a clear departure of that, the horizontal data set. For even more wow factor, I guess, there's that red line that says line-driven winds on it. That is how much material could be responsible, could be chalked up to line-driven winds. And as you can see, it's very not close to the data set. So what we've established is that line-driven winds cannot possibly be the underlying cause for this mass loss episode. So everybody who worked on 2014C said type 1BC supernovae have stuff in its CSM. I've said, for example, 2004C, which was a type 2B, has stuff in its CSM. Other people have talked about superluminous type 1 supernovae. In fact, all stripped envelope supernovae have things in their CSM. I'm not the first to say this. I know everybody who worked on 14C is not the first one to say this. This block quote, I know a lot of you are listed in here. These block citations are also not the first ones to say it. We've known that stuff is in the CSM, but we don't know how it got there. And so Daniel Brethauer, he's a first-year grad student at UC Berkeley, just published a paper very recently that has all of the stripped envelope, and in fact, a few not stripped classes of supernovae, and he compiled all of the mass losses, their rates, the amount of material in their CSM, and how far they are from the star, and that's this plot here. And I don't expect you to read any of it except to see that on the y-axis, it's material, the amount of material, and on the x-axis, it's that radius away from the star. And I've drawn in blue dotted line here what line-driven winds can do. So the punchline is way too much material, very far from the star, not possible with line-driven winds. So I keep talking about how radio data tells me this, but I haven't exactly told you how. So let's say that a star is living its life and material leaves the surface of the star and it's traveling at its own pace away from the stellar surface. And it ends up maybe somewhere around 10 to the 16 centimeters at its own pace. When the supernova explodes, the fastest ejecta moves at about 10% the speed of light, and it quickly encounters that material that was once left by the star in about 40 days. However, we have a distance, and if we assume a speed at which that material left the surface of the star, you actually have a look-back time, and that's how this process works. So the look-back time at 10 to the 16 centimeters, depending on the velocity you choose, looks back to the final hours, to thousands of years of the supernova. That's no exaggeration. It's literally the last hours that the supernova lived its life. And this is the material that you get to probe at radio wavelengths with a nice, comfortable 40 days to go take a look. So coming back to this plot that I had mentioned before from this, the same one that I showed earlier from my paper, Along the x-axis at the top is a look back time if you assume about 10,000 kilometers per second, which is thought to be the wind speed of a Wolf-Rayet star. And so the actual age of this shell, if it was deposited by winds of about 10,000 kilometers per second, is 10 to the 3 days. That's about 3 years right before the star exploded. Once again, Daniel Brethauer did an amazing job of compiling the information in the literature. So I stole this also from his paper. So if you're like me, or if you're like Wynn, the immediate question is, if we're looking at these final moments of a star, what can we say about the inner core dynamics? What's happening at the center of the star during these moments? And so what Daniel did for 2014C, this was with X-ray data actually, he plotted these vertical lines, that's the black lines of where the shell is located, and used some models from Chiot and Quartet 2014 to make note of what shell burning was happening for rotating and non-rotating models. And in this case, I think we end up with helium shell burning. But as you can guess where this is going, because this is an LSST talk, we're going to be able to populate this sort of plot a lot more and a lot easier when you have more data. So I wanted to do another case study of 2016 GKG, which was another type 2b supernova that exploded in 2016, and it also had an appreciable radio signature that pointed to interaction in its CSM. So this I stole from Charlie Kilpatrick's paper from last year, and the point that I've circled in green is just Pan-STARRS data. And a bunch of the photometry has been offset here. So I circled the R band that has not been offset, so you don't have to think that you can trust that for what it is on the plot. And so you see that we were able to follow 16 GKG all the way down to 21st mag, which is about the limit of Pan-STARRS. 2016 GKG was about 26 megaparsecs away from the Earth. And like I said, it had a radio signature in it. If 16 GKG had been located 100 megaparsecs instead, we would have missed a lot of its evolution. So that black line is at 21 mag, which is about the limit of Pan-STARRS and other all-sky surveys. As I'm sure you all know, that the limit of R for LSST is about 25 mag. And so the brown horizontal line that I've drawn down there is where LSST will be able to see. So the punchline of this particular illustration is that LSST will be able to capture 2016 GKG-like events and many other events all the way out to 100 megaparsecs. And because our current surveys are limited by about 21 mag, this is important if we want to see more events like this. But most importantly, at least for me, is that radio observation or radio follow-up normally kicks on at about 40 days. And that's where I've drawn this vertical line. If GKG was 100 megaparsecs away and I started to follow it at 40 days, I wouldn't get much time before it disappeared. In fact, it didn't start interacting with its CSM until 300 days. So had it been 100 megaparsecs away, I might have missed it, or I didn't trigger the follow-up. I think that was actually Maria Drought, but we would have missed it as a community. And the important thing to note here is that there is no radio all-sky survey that's on all the time. Radio strictly depends on constant optical information to follow up on targets, especially targets that are interesting or doing something unprecedented, like late time wiggling in its light curve, or even things like plateauing, even if it's just for a few days. That's how we know that we need to trigger radio follow-up. So in a sense, our radio follow-up has been very limited as a volumetric sample by only close by objects, because these are the only ones that we can follow until late times. And that's the power of LSST, is that not only will we be able to see farther targets, but we will also see nearby targets for a longer period of time, and we can catch CSM interaction as the blast wave actually makes its way out that far. What's also very important about this is that I keep alluding to the fact that all stripped envelope supernovae seem to be exhibiting this kind of behavior, and we don't know why. And so I wanted to leave you with a question: why do such diverse progenitors from these different supernovae all have a very similar death rattle at the end of their lives? Why do they all happen to lose a ton of material in the hours to thousands of years right before their death? This is a problem that I'm thinking a lot about, not just as LSST turns on, but I'm also using the software that created that plot that I wrote to look at type 2b supernovae as a population. Charlie Kilpatrick right now is working on type 2n supernovae to see if we can also parameterize the space. So it's filling in quickly. And with LSST in the Southern Hemisphere, it also opens us up to a lot more opportunities for follow-up and better rates, better population. And I think it can only go up from here. So thank you very much. This is where I stole my art from.
Great job and wonderful visual style for your slides. Questions?
Wonderful talk, Lindsay. My question is about 16 GKG. It's a stripped envelope supernovae. So we are thinking about line-driven winds, but like most of the stripped envelope supernovae, it's rare that stars exist alone in nature. So especially if there is a stripping influence from a nearby companion, binary. So my question is, do these before there is a Rorschach overflow, is there a influence of a binary companion in the mass loss? I don't know. I'm just thinking and asking.
I am so glad you asked. No. So actually, I want to use this plot to answer your question. So okay, GKG was a type 2b. Yeah. And so was O4C. So I'm going to point to a type of plot, but I'm going to use 14C as an example. Okay. If you think of the material in the CSM not just as a shell that was launched all at once, but rather material that was lost at a constant rate, and then maybe at the star, faster winds kicked on, pushed the material further and sculpted something in the CSM, something of a density, that would imply something about the progenitors. Coming back to, is it a red supergiant? Is it a binary? And what could be doing this? And I will definitely say that that part's still an open question. I'm really having trouble picking which slide to show you, but I think what I want to say is that I looked at the material, at least around O4C, for example, and I asked if that material left the star at that speed, how fast would it have had to leave? And what can we say about the size of the red supergiant at that moment? Is it near Rorschach overflow? Is like, what makes sense about it? And so particularly in the case of O4C, in the center of the shell, the material was moving at about 2 kilometers per second. If I assume, for this, I had to hold my mass loss rate constant because there's a degeneracy. But what it works out to is that doesn't make sense as an escape velocity at all. So my personal, philosophy or my personal guess about all of this is that something towards the end of a star's life is increasing the velocity from the surface, and it is creating this kind of appearance. But whether or not that's something fundamental to stellar evolution or something to do with binary evolution, I'm not sure at all. I hope that answers your question.
The best way you could answer. It's the best way you could answer that. Yeah.
Thank you, Bhagya.
Question here.
Awesome talk. So LSST is going to find a lot more stripped envelope things interacting late times, but maybe they're going to be too far and too faint, like or for VLA, right? But maybe not for next gen VLA. Maybe but like say we just have VLA. How will you pick? But maybe there'll be so many nearby things interacting that you won't even know. Maybe there'll be like a tidal wave, or maybe there'll be a drought. Like what do you see? And if there is, how do you prioritize? Say you had all the VLA time in the world to follow up every stripped envelope supernova that's plateauing and clearly interacting because of LSST, and you want to see the synchrotron in VLA. How do you pick?
Yeah. I'm going to preface this by saying I hope I have this problem because when I worked out the rates, I think that the amount of stripped envelope supernovae, the rates from like Lee 2011, I think for within 100 megaparsecs end up to be about 50 per year. But then when you factor in how many actually get spectroscopically classified, and then how many of those spectroscopic, so that's, I think, estimating like 30%. And then how many of those do we end up seeing at current limits interacting, works out to be about 10% of that 30%. At the end of the day, it's like 1 or 2 per year. Because then you think, so, like, what hemisphere can VLA see? So visibility to the VLA particularly really ends up being about 1 or 2 per year. So if you put LSST in the southern hemisphere and you work out the overlap between what LSST can see and what VLA can see, kind of doubles it to optimistically 3 or 4. So I don't think we'll have that problem, but that's all contingent on my 10% that I just quoted before. So like I said, I hope we have that problem. But pretending that we do, I would say things that wiggle dramatically are probably a great source to go after. Yeah, that's my best guess.
More questions? Oh, not to mention that, we will have very, very few spectroscopically confirmed 2Bs from Will.
And that's actually a perfect segue. So if we have really, really small number statistics from Blueprint in reality, a lot of what we're doing in film noir is looking at the chalk mark outline of the dead body, in this case, the supernova, and then trying to figure out who done it, right? So why not go just look at the stars in the galaxy itself? Why should we not be doing a survey of Wolf-Rayet stars or, systems like the A38 Mon?
No, I think so. I want to be careful how I answer this, because if there are people who work on this and I don't read their papers, then I'm already very sorry. But this is something that matters a lot to me, especially about the progenitor question, because what it could be is a very short-lived Wolf-Rayet phase right before it dies, where you have this like uptick in velocity, wind velocity, that's sculpting the CSM super nearby the star. But you already see Wolf-Rayet stars in nature, like, long-lived. So something's not adding up. And I think that that's another amazing way to start answering the question is like, what do we actually observe about the life and times of Wolf-Rayet stars? Yeah.